Well, we're right at the top of the hour, and I think we've got a lot to cover, so we're going to get started. And so welcome everyone to the Rohde Schwarz MXO4 virtual demo. We're excited to do this today. We've got some speakers from Rohde Schwarz here, so we're going to get started. So welcome everyone, and welcome to our presenter, Greg McCaskill from Rohde Schwarz. Good morning, good afternoon.
Thank you, Steve. Good to be here.
Yeah, so Greg is product manager for scopes at Rohde Schwarz and for some time, and I'm been in marketing now, but it was an application engineer and things. So I've been using scopes for a long time. So this is going to be some fun. But first, before we get started, I'm going to have a little brief commercial about Electrorent. Electrorent is a very large technology provider, primarily test equipment all over the world. We have offices in Los Angeles, London, Penang, China, India, and can get equipment to any of those spots in the world. We have a lot of Rohde Schwarz RF equipment. Today's equipment, though, is we're selling new, the MXO4 series scope. And right before we get started with Greg, your presentation, I'll just explain that I will be looking at the questions for folks. So you could type it into the questions section of the webinar, and I will get the questions over to Greg. And so with all that, Greg, I'm gonna make you the presenter here so you can show your stuff.
Perfect.
Hang on a second.
Okay, Steve, if you can do me a favor, let me know when the slides show up on your end.
You are good to go.
Okay, very good. Hi, everybody. Greg McCaskill here with Rohde Schwarz. I'm an oscilloscope product manager with Rohde Schwarz. I've been part of this organization for about 10 years. I'm based in Austin, Texas. I'm currently in our Columbia, Maryland, U.S. headquarters. But good to be here with you today. And we're going to be talking about the MXO4 oscilloscope. I'll show you a presentation followed by a demo to show you some of the features and how those will benefit the measurements that you're making. So before I get into the instrument itself, I did want to give some background on some of the key terms because I'll be talking about the features we've implemented, but I want to give some background on those terms. And then we'll do an overview of the product itself, and then I'll get into a key benefits demonstration. And finally, we'll do a Q&A. All right, so some of the key terms we want to look at are fast update rate, low noise, deep memory, digital trigger. You know, you might think all triggers are digital or wonder what that term means, and we'll touch on that. We'll look at spectrum, which is also called FFT, and the smart grid, or the user interface. So first, fast update rate, and this is all related to acquisition rate. And so if you look at this graph along the bottom, there's this total acquisition time, and that includes the acquisition and something called blind time. And the acquisition rate is how quickly a scope can trigger, process, and display sequential waveforms. It's specified usually in waveforms per second, and the higher, the better. It's also called update rate or capture rate, and a smaller blind time shortens the acquisition rate and increases, it shortens the acquisition time, and that increases the acquisition rate. So you end up with more waveforms per second. So that's what we're describing when we talk about acquisition rate. How does acquisition rate help reduce test time? Well, it gives you better signal visibility. It gives you a higher probability of capturing rare events. It improves the responsiveness of the oscilloscope. And you get statistical confidence faster because you're compiling data much faster. So the second term is low noise. So how does low noise benefit us? In this example, you're seeing a glimpse of what, in this case, it's a sine wave, but there's some kind of features riding on top of that sine wave. And because of noise, you're not able to see the signal detail. And then on the right side, you can see with the lower noise, you're able to see more of the details of the signal. So where do we look if we want to reduce noise in an oscilloscope? There are three primary elements, and they're all part of the oscilloscope's front end. One of them is the analog to digital converter. There's the variable gain amplifier. There's an analog filter, and I already mentioned the A to D. So these are the three elements, and the first two in that chain are really related to a good front end low noise design. And then the last, the A to D, this is related to how many bits in the A to D and the quality of that A to D. And we're going to talk about that a little bit more. So the smallest voltage difference that an oscilloscope can measure is related to the number of ADC bits. And as you increase the number of ADC bits, you decrease that delta in voltage that you can measure. So if you start off with a 1 volt peak-to-peak signal, for example, the delta in voltage that you could measure with an 8-bit scope at its best would be 3.9 millivolts. And with a 10-bit scope, because the quantization levels, you'd be able to get to 1 millivolts. So the advantages of a higher number of bits is lower noise. And that's the main benefit, I'd say, in this case. And there's also the ability to see small signal details, improves dynamic range, and you have a greater measurement repeatability. So how can you improve vertical resolution? The first and most obvious way is increasing the number of ADC bits. Averaging is also a way of increasing vertical resolution, but the trade-off there is that requires a repetitive signal. You could use high resolution mode, but the trade-off there is sample rate and then also bandwidth. It can be kind of hard to determine what bandwidth you're trading off, but you trade off both of those in high res mode. And finally, there's high definition mode, and this one also has a trade-off. You trade off bandwidth for resolution, and we'll talk about how that works here. So for high definition mode, it's a low pass filter that's placed after the ADC, and that improves the resolution in real time. This is implemented in an ASIC. So the bandwidth is reduced, and you improve the signal and noise and the vertical resolution. And you can improve the number of bits by up to 18 bits total. It does not require a repetitive signal. And one of the other benefits here is it doesn't reduce sample rate, doesn't slow down processing, and you can also use this new high resolution signal as part of your trigger decision. So looking at this signal again, with and without high definition active, it's difficult to see those signal details. You know, we're really looking at just a portion of the overall capture. And now with high resolution mode, higher number of bits, you're able to see the signal details. So deep memory, number 3, really with deep memory, the main thing to remember is you can capture more time. And of course, you know, pretty much any scope, you can crank the time base and capture more time, but the subtle trade-off there is the sample rate will go down because memory is the number of sample points that you can store. And if you don't have much memory, you crank out the time base, you'll decrease the sample rate. So here's an example of that. This is a 400 millisecond capture, and with 1 megapoint of memory, the sample rate has to be reduced. You can see the signal's distorted in that zoom window, and with 800 megapoints, you have a properly sampled signal that can be reproduced accurately. So digital trigger. Okay, this is an interesting one. So what are the effects of trigger sensitivity? And this is, the trigger sensitivity is at the core of the benefits of a digital trigger. So you can see the trigger level, which is the blue dashed line. The trigger sensitivity is this purple area. And that's because triggers are historically analog circuits. And so they're going to require some amount of voltage swing for the trigger to be identified. And so in this case, with these 2 pulses, only the first pulse is able to make it through that trigger sensitivity level and create a trigger event. If you're able to reduce the trigger sensitivity to a very, very small value, then you can trigger on basically any voltage swing. And that's what digital triggering allows you to do. So here's the difference between analog and digital. Analog is going to be a separate path from the ADC, and it's going to have a certain amount of trigger sensitivity that you cannot overcome. It might be half a division, it might be more. A digital trigger is after the ADC, so it uses the sample points for the trigger decision. So your trigger sensitivity is only a little bit greater than your ADC resolution. Okay, let's talk about the superior spectrum. This is another thing that you'll want your scope to have. And this is also called FFT. And so I'm just going to show a few examples of how FFT is used on scopes. One is to see rapid frequency changes. Another would be to detect frequency content that where the time domain just looks like noise, just looks like a flat trace. Another is to find hidden signals. Scopes are great for this. Another is to maybe look at a clock. In the time domain, you can't tell if this is clean or if there's some noise or spurs or something else. And so here in the FFT, it looks good. I'll give you a second example where in the FFT, you can see clearly there are side bands at these offsets. So not easy at all to detect in the time domain, but the frequency domain really gives you this capability. And the last thing I'll touch on is the smart grid or the user interface. I'm really excited about some of the things we did in the user interface. If you've seen scopes lately, they have large screens. They're very interactive from a touch screen perspective. We've added nice box design. So even if you have big fingers, it's easy to touch in the right place. The cursors actively show dynamic values. And there's even a search box in the menu. This one is in German, but of course the scopes are localized for the US, and that would normally say search, and you can type in whatever you want there. For example, if you wanted to change the color of a channel, you could type in the word color, and it would lead you right to the menus, similar to your smartphone. So how's the smart grid broken down? We have things like a toolbar that's completely configurable for your favorite measurements. The trigger, the horizontal, and the acquisition systems, you can see the settings and you can access them simply by touching any of those boxes. You can open up math or additional channels simply by touching these activators, and the menu is also conveniently located in the bottom. And you can see that all of that is out of the way of the main display, and it's nice and wide and long. And if you want to reorganize your display, it is simple as touching one of these icons on the bottom and dragging it to the location on the screen where you want it placed. Perfect. So a little bit about the product itself that we're going to demonstrate. It's the MXO4, and it's a product that goes up to 1.5 gigahertz. We would say this is in the 4 series class of oscilloscopes. It has a lot of memory, comes standard 400 megapoints of memory. It's a 12-bit ADC and 4.5 million waveforms per second. That 4.5 million waveforms per second is an industry first. Scopes up to this point, the max that anybody has provided has been 1 million. And it has 12 bits and up to 18 bits. You might have heard of 12-bit scopes before, but we were the first with an 18-bit scope. And lots of memory in the digital trigger that we mentioned earlier, plus 2-channel ARB, and the MXO is standard built in. All you need to do is connect the probes. So if you have multiple of these instruments, you can move the probes around. On the back, we have some nice connections to things like HDMI and LAN. And I mentioned FFT earlier. In this case, the MXO has an incredibly responsive FFT, greater than 45,000 FFTs per second. And it comes with Rohde Schwarz Smart Grid. Another cool feature to keep your desk clean and clear is a VESA mount. And VESA mounts, you can get these anywhere these days. Most people already have one on their desk for their monitor. This is a standard 100mm VESA mount. So next I'm going to do the key benefits demo. So bear with me for a second as I see. Okay. Closed. So I'm going to access the scope just over a web browser. And there are two ways of looking at this on the web browser. I can show the side panel so you can see the scope that's sitting in front of me has a very large touchscreen, but of course it still has a full side panel with knobs and buttons. And for example, if you turned on channel 2, you'd see that these rings turn green, and then I'd be adjusting channel 2 and 3 and 4, etc. I'm going to preset the scope, and I'm going to turn off the front panel and let's focus just on the screen itself, and I'll give you a demo of some of the key features. So the first one that we were talking about was fast update rate. And in this case, I'm showing a signal that has some rare events. They're happening once per second. And at typical update rates in this class of oscilloscope, you're not going to see rare events that happen once per second. Statistically, it's challenging to find those. If I turn off the limitation that I had implemented and turn up the intensity, you'll see those pop up from time to time in the background there. So that's one of the benefits of a really fast update rate. And I can show you the acquisition speed here. And it's, and with these settings, it's over 3 million waveforms per second. And it even shows you the percent of time captured. So it's really nice to know that these things change with your setup. And this is incredibly fast and very little blind time. Another way to think about fast update rate would be changing signal behavior. So in this case, the signal has AM modulation. And you can see that that's happening, but with a typical scope update rate, it's a little bit erratic. If you look at this with the performance of the MXO, you see the full behavior of the signal. That's another benefit of fast update rate. For low noise, a nice way to look at no noise would be no signals connected, and turn up the volts per division. So in this case, we're at 500 microvolts per division. You can see that down here. And the frequency domain with a full span all the way out to 1.2 gigahertz. You see it's nice and flat. It's down at 95 dBm, no spurs. So really good noise performance. Here's a different way to look at low noise. I showed you this signal in the PowerPoint earlier. So in this mode, we're currently in 12-bit mode. And you can see that there's some kind of feature on there. If we want to reduce the noise further, we can turn on HD mode. And now you can see we've gone to 18-bit mode, and the details are shown. It's updating really fast. So let me push single, and you can see that small sine wave riding on top of the larger sine wave. So not only are the analog components in the scope low noise, but you have a high number of bits, in this case up to 18, so you can really see fine details. So for deep memory, one of the limitations that we talked about earlier is you take a really long acquisition, and if you don't have enough memory, you'll undersample. So in this case, I've provided the scope with about 32 megapoints of memory only, and we're capturing 2 seconds of time. And with that, you can see that the signal edges are probably not as fast as I would expect. So if I was measuring something like rise time here, I wouldn't be getting an accurate measurement. And there's lots of ringing, which really tells me it's not sampled enough. So let me show you with the memory available on the MXO4. Now we're using over 700 megapoints and you can see the edges are sharp, the ringing is gone, and so even with a long acquisition, my measurements are going to be accurate. If I was doing protocol, trigger and decode, I'm going to sample enough to correctly decode those signals. Number 4 is the digital trigger. So I'm gonna move the trigger level up and down so you can see where we are. So we're currently triggering on this big pulse, and we talked about how analog triggers are going to have a sensitivity that might be, a half a division or more. And so one of the things is you might have an input that has large components and small components, and if you want to trigger on those smaller components, you can't just turn up the volts per division to make them larger. You're limited to your settings, so your trigger needs to be sensitive enough to scroll down and trigger on elements like this. And this one, okay, this is maybe a little bit bigger than half a division, but what if you wanted to trigger on that next one? In this case, we've turned on HD mode, and you can see we're triggering on this smaller pulse, and you can even trigger on the even smaller pulse. So to take it perhaps even a step further, I'm going to trigger on the rising edge of this undershoot here. So this is where we're triggering right here. And this is something that's completely impossible on an analog trigger, to trigger on the finest details of your signal. So if you're really looking for something on your signal, if you can see it, you can trigger on it. Here's another way of looking at that trigger sensitivity. So you see that sine wave riding on top of the larger sine wave. I can move the trigger level up and down, and we are triggering on this very small rising edge, no problem. So even with this kind of condition, the trigger is consistent. Superior spectrum. Other scopes in this class are going to be about 10 FFTs per second or fewer. And so if you have a dynamic signal such as this one, I think I've got this updating about 500 FFTs per second. And you can see that signal is walking over, but you're really not seeing the full dynamic behavior. If I remove that restriction and show you the full performance of the MXO, you can see that you're able to keep track of this frequency modulated signal and see the dynamic nature of things. So with this kind of performance, you don't have to second guess what might be happening. You can see what's happening. Another common application for FFTs on scopes would be EMI debug. And in this case, I've just got a square wave coming in, but to show you some of the nice features of the FFT, you can have a peak list. You can also turn on things to show, for example, the peaks on the waveform itself. So that's pretty cool. And finally, the last thing I wanted to show you, part of the demo, would be the smart grid. So this is where you have signals and you can either kind of move them around all on one grid, but really you're going to want to place things in different locations to understand your scenario, right? You're debugging or you're measuring, you're trying to make sense of some kind of condition, and you want to be able to move things around the screen and organize them in such a way that you can make sense of your data. And with the smart grid, you can move them anywhere you like. You can pile them on top of each other. You can move them next to each other. And you can do this with math traces, reference traces, spectrums, and things like that. So it's very nice to be able to quickly move your data around. And I talked about the toolbar earlier. That's up here with things like Zoom. I used Zoom earlier. You can add your favorite tools, and here's an example of all the tools you can add. You can reorder where they are, so that's nice as well. Okay, Steve, with that, I think I'm at the end of the demo and the presentation.
Oh, well, that was great. And we do have time for some questions, but So go ahead and put them in the question section if you've got those. But I noticed something, Greg, is that what you didn't mention was that, you know, when you're doing those signals and showing us all those features, those are built-in demos that you can actually toggle through, because I recognized some of them there. So those were where your
Yeah, exactly. So
your ARB channel is connected to channel 1 internally. You don't even need a cable. And so anybody that's wants to remember how something is done or go through a feature, those are instantly available. You just hit a button on your the applications screen, and you can see all those features. It makes it like a really quick walkthrough of all the advanced features. I thought that was pretty good.
thank you.
Yep.
Yep.
The other thing that you didn't get to see was I did love the smart grid and dragging my finger around on the touch screen, but I'm kind of like I like the hard buttons. And to get to the a lot of things that was really you know, like the trigger source, for example, toggling the trigger source changes the color of the of your potential trigger source. You know, right now you've got 2 channels, channel 1 and channel 3, and toggling that trigger source is like it changed color. It was like, oh yeah, of course. It's you know, you wouldn't expect that, but it was a very nice feature to go. And I don't see any other questions, so I am going to wait around just for a second because I do have the handouts to give to folks. Hang on a second. I'll put that into the. So the handout section now has the handouts of all the slides, and don't see any other questions. But this is awesome. It worked out great to see all of the live demos on the screen and the great explanation. So thank you very much. And with that, I think we're just going to end the webinar. Greg, really appreciate the showing of the scope. Thank you.
Steve, thank you, and to ElectroRent for having us today, and thanks everybody.
All right, see everybody later. Thank you for attending. Bye, Greg.
Bye-bye.